We know that our total wave function can be written down as a position-dependent part and a time-dependent part. And for the infinite square well, we know that the position-dependent part, which is psi of x, has a general solution that looks like the square root of 2 all over a times sine n pi x all over a. But what really is the case is that since the energy levels are positive integers, your total wave function, that is the position dependent part, can be expressed as a linear combination of all of these. What I'm trying to say is that the wave function that has the position dependence can be assumed to have different energy levels depending on what the value of n is. So psi of x, which is the stationary states, can be written as a linear combination of all of them. And therefore we write and notice that these c sub n's are what we call the coefficients of your stationary states. These coefficients, when we take their absolute value and we square them, these tell us the probability of measuring energy E sub n of that particle having that specific wave function. For example, if we have a particle that starts out with the following wave function, then over here, this means that the probability of measuring E sub 1 is 3 all over 5, is 3 all over 5, the absolute value of which squared, which is 9 over 25. Similarly, this also means that the probability of measuring E sub 3 is 4 all over 5, the absolute value taken squared, which is 16 all over 25. But the probability of measuring E2 is basically 0 because our wave function doesn't have a psi sub 2. Also, one important thing that you can also notice over here is that the sum of all absolute value of c sub n squared should equal to 1. You can also notice this over here in this case, where our particle started off with this particular wave function, and if you take the sum of the squares of c1 and c3, you get that 9 all over 25 plus 16 all over 25 is 25 all over 25, which is basically 1. Yeah. So now that we know the significance of finding these coefficients, which is c sub n, let us now try to find these c sub n's. How do we actually know what our c sub n's are for a very specific wave function? Well, a very useful technique is to use the property of the stationary states that all stationary states are orthogonal to each other. This basically means that taking the inner product of the stationary states with each other gives us the Kronecker delta function. The Kronecker delta function is defined as such that the Kronecker delta is 0 at all points where m is not equal to n, but it is 1 where m is equal to n. So with this property, our stationary states being orthogonal to each other basically means that if you take the inner product, which is in Dirac notation, if you take the inner product of them, then the integral of these two specific stationary states would give us the Kronecker delta. And with the help of this property, we will find our c sub n. But how do we actually do that? Well, recall that psi of x comma 0 is basically a linear combination of all the stationary states that are possible. Now, let's assume that the possible stationary states that are possible for our function, for our particle over here, extends up to some integer k. And we want to find a very particular coefficient, which is c sub n all over here. All right, so how do we find what this c sub n is? Well, what we basically do is the entire collection of terms to our right over here, we take the inner product of that with psi of n as a function of x. So what we are basically doing is we're taking the inner product. And when we take the inner product, we have that we take the inner product of psi of n of x with the total wave function, which is psi of x comma 0. And we have the following term in the right over here. So this is what we got in the right-hand side of our equation over here. Now notice that these C1, C2, Cn, Ck's, all of these C's are just constants, right? So we can all pull these things out of our inner products, right? So after we do that, we have some inner products, some individual terms left in our right-hand side of the equation. Let's work with one case first, the very first term over here first, and then we will carry out what happens to the other terms in the right. So for the case where we have that C1 psi of nx dotted with inner product with psi 1 x, we have that we have to evaluate what this term basically means. But notice that the property of orthogonality, which is this, basically says that when m is equal to n, we have that the conical delta function is 1. But when m is not equal to n, which is this case over here, our conical delta function is basically what? Is basically 0. So in this case, we have n, right? And we have 1 over here. We know for a fact that in this case, n is not equal to 1, right? We have another term over here where n is basically matching to another term, which is n in the right-hand side. So definitely, this entire term, this inner product over here, is 0, right? So this entire term goes to 0 along with the C1. And similarly, we could say that all of these other terms in the right-hand side, the first term, the second term, leading up to psi n, which is this term over here, all of them leading up to this is 0. And all of the terms leading up to psi n, psi k, their inner product, is basically 0, right? So all of them is 0. All of them are 0. So this entire right-hand side just only becomes, 0 plus dot 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 Cn psi n plus 0 plus dot 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 leading up to 0. And we're basically left with Cn psi n. I should add that this is a function of x. And yeah, this is basically it. So going back to our orthogonality property of stationary states, we have that when m is equal to n, this case over here, your conical delta function gives you 1. In this case, definitely n is basically equal to n, therefore we can write that this entire term is 1, and we have that the inner product of psi n x with psi x 0 is basically c sub n. So this is how you find out c sub n. So for the infinite square well, specifically, we can find out c sub n in the very same format. And when you do the integral, you have that the integral has the bounds from 0 to a, and inside you have the square root of 2 all over a sine n pi x all over a times psi x dx. And of course, you can pull out the square root of 2 all over a outside, and you have that this is basically looking like the following format over here. And voila. And this is how you find out the coefficients for your stationary states for any given wave function.